Hi everyone, good afternoon or good morning, depending on where you are. My name is Markudova, and I am from the Polytechnic University of Turin. I'm a PhD student there. And today I will present our paper, which is called What's My App? And it's a machine learning-based classification of real-time communication applications. And this study was developed together with Cisco Systems in France. And it's a part of a bigger project that we are doing with them on quality of experience of RTC applications. So until now in this workshop, we had a quality of experience of web applications, we had streaming video, and now let's go to real-time applications. All right, so the content of my presentation will be the following. First, introduction, why classify real-time applications. Then what is our system architecture and our methodology. Then I'll present the results that we got in our case study and of course some conclusions and next steps. All right, let's start with the introduction. So the motivation, as you can see, even at this moment, we are doing this conference on Cisco WebEx meetings, and it's what we've been doing all year in response to the coronavirus pandemic. So we can see that real-time communication is becoming increasingly important, so for both business and leisure. And so we feel that a better quality of experience is needed here to have seamless video calls. And actually the goal of the project with Cisco is to encourage network management policies that favor quality of experience of online meeting applications. And the first steps towards this is actually to regain visibility on this kind of traffic and to shed light to the network control plane about what is going on with RTC in the network. So are there any meetings going on? What are the employed applications? What is the perceived QoE? Etc. And we feel that knowing the employed application could be important to have maybe different network management for different kind of apps, like some of them are used for business, some of them are used for leisure. So this could have numerous, there are numerous possibilities of what to do if you know the meeting applications. All right, so what is the scenario here? We have, let me try to have also the laser here. So we are doing a conference call, and we are at the client side and we capture this traffic. And the idea of the application of this system is to be at the network, so to be in an intermediate router. But the case study we did, of course, is we capture the traffic at the client side. So then we have some kind of RTP traffic. It's actually easy to distinguish what is the RTP. You can do it with Wireshark. For some apps, not so much, but okay, it's still easy to do. And then we have our system, which is basically telling us what is the application that was being used. So that is the goal of the system. We want to know what was the meeting application that generated this RTC traffic. And actually, our system is able to tell us what was the application even a priori. And we'll talk about this in the next slides. This is a powerful feature. All right, so what is the methodology of the system? Well, here is the system architecture. So first, of course, we have all our packet traces, and I will talk in detail about all these 4 steps. And then we extract the meaningful information that we need from these packet traces, which for us are the domain names that are resolved before starting the call. And this is how we can know even prior to starting the call. And then these domain names are actually, letters. So we want to convert them to a machine learning friendly feature matrix. And here we borrow a technique from natural language processing, which is called TF-IDF. And we make our feature matrix, which we plug into our classifiers, and we use one versus rest classifiers. So let's take a look at each of these steps. Well, first, the packet traces. Actually, we collected around 240 traffic traces from 15 volunteers. And basically, during the lockdown from March to May 2020, we asked our colleagues to capture all the meetings that they will be doing. So this is real, let's say they are real traffic traces, not just in such a controlled environment. And we selected 5 meeting applications for our case study, which are Jitsi, Microsoft Teams, WebEx Teams, Zoom, and Skype. And this is the overview of how much data we have on each of them. And then, as I said, we were doing our bag of domains extraction, so to extract the meaningful values we want from our pickups. So we went into TLS, the handshake of client hello, and we took the server name indication extensions. And actually, here we see if we have an RTC session that we were taking a look at some delta t time before the call starts, and we were taking the domain names. So they look something like this. If we have a Zoom call, we have this kind of domains, which end with Zoom US. But if we have, for example, Skype open in the background, we could also see some domains resolved for Skype, which is noise for our application. We will see later that our system is able to mitigate this. So this is our bag of domains that we input to our feature matrix. Our feature matrix looks like this. We use the NLP technique TF-IDF, which means term frequency times inverse document frequency. So basically, every row of the matrix is one RTC session, and every column of the matrix is one domain name. And these domain names are actually taken from all of the sessions of the training set. And the term frequency is basically the number of times the domain D occurs in this call. And inverse document frequency, it tells us how rare the domain is among pickups. And basically, we don't want domains that only appeared, for example, in one pickup or that appeared in all of the pickups because they are not informative for us. So here we introduce a second parameter, which is called mean frequency, which means keep only domains that appeared in at least mean frequency of the documents. All right, and then we have our feature matrix, which we can plug for classifier. What we do is we feed one binary classifier per class. So for each classifier, the class is fitted against all the other classes, which means we have one classifier which says Skype or other, another one which says WebEx Teams versus other. And I'll tell you the advantages of this approach later. The train test method that we use is also particular because we have traffic from different volunteers, and different volunteers produce different kind of noise. So while they're in call, so we try to train with calls using one set of people and test with calls with another set of people. Because otherwise, if there's one person who's always reading the news while they're in call, then maybe our system will learn that this means that they're using Skype because they were always using Skype. Right, and as algorithms, we use classical classification algorithms like decision tree, random forest, k-nearest neighbor, support vector machine, and Gaussian naive bias, and we compare their performance. We use the implementations of scikit-learn. All of our code is written in Python, and to extract the DNS domain names, we use Tstat, which is a tool that we developed in Polytechnic of Torino some years ago. And then we also use these performance metrics, which are the classical ones, the confusion matrix, the precision recall F1 score, and the accuracy. All right, so what are the advantages of this kind of approach? Well, first, we use data exchanged prior to an RTC session, so we can classify new streams with virtually no delay. So this application is meant to work online. And we do not use statistical properties of the traffic, which means we are robust to different protocol implementations. Here I put a star because this could also be, statistical properties are powerful in another sense because they can give us statistical signatures of the apps, or if TLS gets encrypted, we can use them. And we'll talk about this in our future work. Then this approach with using domain names is also more robust than using mere DPI, like using IP addresses or ports, because we saw in another study that we did a comparative study of RTC applications that large companies nowadays, they rely on CDNs and cloud providers to relay the media traffic, and that also applications make use of peer-to-peer whenever possible. So these kind of approaches would fall short. And what are the advantages of using one versus rest classifier? Well, first, it can be used in the wild. So if we give it any other meeting application, it would place it in the other category of all the 5 classifiers. And it is interpretable, so we can examine each classifier and learn about that class, as we will see in the results. It is also scalable because we can add as we want more classifiers for more meeting applications, and we can parallelize the code. All right, so what are the results that we got in our case study? Well, first, this is the best performing result, which is a random forest with as little as 100 trees, which takes into account domains that appeared in more than 3% of the pickups and that it appeared 25 seconds before the call starts. So here we can see that we have pretty satisfactory results because we have an overall accuracy of 87% and macro average F1 score of 0.89, and here are the F1 scores of all the classes. And what we can just see is that the precision of WebEx Teams is a bit lower. It seems that a lot of applications are being confused with WebEx Teams, and this may be due to background noise because maybe a lot of the clients in our data set were using other applications while talking on WebEx Teams. And here are the feature importances of each classifier. Here we can see the interpretability of our approach. So this is the classifier Skype versus other. This is Microsoft Teams versus other, Zoom versus other, Jitsi versus other. And we can see that the importance that it gives to the applications and domains that appear are actually meaningful. So we have Skype.com, Microsoft.com. As you know, Skype is owned by Microsoft. So here in Microsoft Teams, we also have domains teams.microsoft.com. And for Jitsi, we can see that we have Meet Jitsi, which is the most important one. And then we have some other noise, but Random Forest is really able to mitigate this because it gives a lot of importance to Meet Jitsi, which is the most important domain. And for Zoom, we can see the same thing. It's able to really see what are the meaningful features. Okay, so how sensitive is our approach to parameters? Here we see a combination of the 5 algorithms and the different values for delta t, so the seconds considered before RTP traffic starts. And we can see that first, the larger the delta t, so the more domains we let in, the better performance we get in general. Then we can see that for each algorithm, we have different things like KNN, which is better for a smaller delta t, decision tree, and SVM, which are these, and these show in general a good performance. Also, Gaussian naive Bayes shows excellent performance. And but the best result is, as I said before, gained with Random Forest for the 25 seconds before delta t. And yes, this is what we see in general. Then, if we want to take a look at the parameter sensitivity of the mean frequency parameter, here we vary the mean frequency parameter and we take a look at what number of features we have and what is the F1 score. So, as we can see again, the smaller the mean frequency, the more features we let in, the more domains we let in, the more features we use, the better performance we get. And we can see a cascading behavior with 2 main jumps, which basically we have the first jump at 4 features, so with as little as 4 features here, this, we have an F1 score of 0.55. And with as little as 9 features, we have an F1 score of 0.85. And our best one is 0.89. So we are kind of in a saturation situation as little as 9 features, which is powerful. And so the conclusions in the next steps. Well, in conclusion, we saw that our system successfully classifies 5 meeting applications. It can work in real time. That's how it's designed to work. The computation, as I said, can be parallelized. It is able to mitigate noise from other domains because, as you saw, our data set was made in the wild because we didn't ask people to turn off other applications while they were collecting traffic. And another powerful thing is that it automatically constructs features, so there is no need for domain experts. It can also work using multiple algorithms with small variations of performance, as we saw when we were comparing them. So if you don't want to use Random Forest, feel free to use Gaussian naive Bayes. It's more simple for you. And it works well even with a small amount of data, because we saw we had 240 pickups, each translated into 1 line, basically, of our feature matrix. So we had just 240 data samples, even though we had so much data for 240 meetings due to the construction of our system. But in the end, it works well with this small amount of data, so it's okay. And as future work, actually, we would like to try classifying meeting applications using statistical features of traffic, or because they can act as statistical signatures of applications. Because, as I said, TLS might get encrypted or it might get obsolete, and we want to be robust to this. Then we also want to expand to other applications, other meeting applications, cloud gaming, etc., which is easy to plug in, but we need to also train those classifiers. And in the end, having all this, we want to test in a big mix of ISP traffic and see how our system will respond. All right, so that's it. Thank you very much for your attention.
Thank you, Dana. I think very timely topic.
Yeah.
And questions for Dana? I hope you didn't fall asleep.
No. So thanks for the presentation. I actually have a question regarding your future work.
Yes.
So you mentioned that you would like to classify meeting application using other statistical features. I guess this is related to the fact that you will have also the DNS encrypted in the near future, so you might not be able to use the same feature as now. About that, I have one suggestion, let's say, and one question at the same time. The question is, are you thinking about looking into using a deep network solution to solve this kind of issue, because then you might have less problem regarding to the future. But this, on the opposite, is the suggestion if you are still running some captures, because of course for deep learning application you need a lot of label data, so running the capture is very important.
Yes. Well, to be honest, for now, I prefer interpretable approaches. And as they say, doing a simple solution to a complicated problem is always more difficult. Or we are just lucky that a random forest can work for our problem. But yes, it may be a good idea to try also if we see when we are able to collect more data, which now being in the second lockdown may also not be a problem. And if we see that a neural network may work better on it at the point when we have a lot of data, this could be a very good idea. And I think that if we go to statistical features, they would be much more features and much more complicated and more, let's say, also not so interpretable. So the interpretability would not stay such a big thing. And then we could freely use neural networks for this. Yes.
Thank you, Dana.
One thing related to this is that if your features are basically each website, each DNS domain, if it's present or not. And when in these kind of problems, from my experience, it's true that even a simple TF-IDF approach is working quite well. Also, given also the direction that maybe in the future DNS will be encrypted, one thing is, why don't you exploit the information about the sequence, the order? Because here you're just actually taking a window that you tune and putting everything inside. But I guess that also the series of event is important.
Yes, I totally agree. And this is a discussion that we also had in the beginning, that we would like to, if needed, to go into the temporal sequence of things, because this can also help. And yes, this is a great suggestion. Thank you. We were thinking about it for now. We tried this as a first approach, but in the future, I think it would be really useful.
Okay, thanks. Other question for Lena? I guess no, so thank you, and we can